The Great Pyramid stood as the world's tallest structure for over 3,800 years. How did ancient builders achieve this without steel or machinery? This video reveals the specific technological breakthroughs that allowed early civilizations to construct their towering monuments. You will learn the exact methods and tools that turned stone and ambition into timeless wonders. We will explore how they moved multi-ton blocks and achieved impossible precision with only simple tools. Their secrets, from forgotten ramps to revolutionary measurement systems, reshaped our world. What do you believe was the most crucial ingredient for these ancient marvels? That ambition to build upwards was more than just a dream. It was a complete transformation of human society. Before the first stone was ever set, a revolution had to occur in the minds of the people and the structure of their communities. Think about the shift from building a home for a single family to coordinating a project that would take generations. This required a new kind of belief, a shared vision powerful enough to convince thousands of people to dedicate their lives to a goal they themselves would never see finished. It was a leap of faith made visible in stone. What kind of societal engine could possibly fuel such an undertaking? Often, it was a fusion of deep spiritual devotion and centralized political authority. A ruler or a priestly class could unite a population under a common purpose, convincing them that constructing a pathway to the gods was a sacred duty. This collective endeavor demanded unprecedented organization. For the first time on such a scale, societies had to solve problems of logistics. They needed to feed a massive, non-farming workforce. They had to establish supply chains for materials, sometimes from hundreds of miles away. They had to create systems for managing time, labor, and resources with a precision that was entirely new to the human experience. This was the true first breakthrough, not a tool of wood or stone, but a tool of the human spirit and social ingenuity. It was the invention of large-scale cooperation itself. Without this foundational shift in how people worked together, the pyramids would have remained mere sketches in the sand. This collective will set the stage for the physical inventions that would soon follow, the clever engineering that turned shared ambition into immortal stone. That simple weight on a string, the plumb bob, was a silent revolution in the builder's hand. For the first time, an architect could defy the fallibility of the human eye. Gravity itself became their guide, a force that never lies, ensuring that every stone they set was aligned with the center of the earth. This was not just about making walls look straight. It was about survival. A tall structure with even a slight lean creates immense, unbalanced forces, dooming it to eventual collapse. The plumb bob, along with its companion tool, the water level, which used the unwavering surface of water to define a true horizontal plane, gave builders the power to fight these invisible pressures. They transformed abstract concepts of vertical and horizontal into physical, tangible realities that any worker could understand and follow. Think of the confidence this must have inspired. A team could now build upwards with the certainty that their work would endure, that their grand vision would not crumble under its own weight. This fundamental need for consistency did not stop at a single building site. If you are bringing stone from quarries miles away or coordinating teams of hundreds, how do you ensure every piece fits? The solution was a new language of creation, born from the quest for perfect alignment. This new language of creation was a system of measurement, a shared vocabulary for size and shape that every worker could understand. Imagine the chaos without it. One team cuts a block based on the length of their foreman's arm, while another team, miles away, uses a different standard. The stones would arrive at the building site as a jumbled, useless puzzle. To build a perfect pyramid, every single block had to be a perfect, interchangeable part. This is why the cubit rod was born. It was not just a stick, it was a master key. Typically based on the length of a man's forearm from elbow to fingertip, this standardized unit was reproduced on wooden or stone rods and given to overseers across the entire operation. A quarry worker in Aswan and a mason at Giza were, for the first time, speaking the same precise language. They were now building with numbers, not just stone. But measurement alone was not enough. The true magic happened when these numbers met geometry. The simple, profound truth of a right angle, the predictable strength of a triangle, these were the invisible blueprints. An architect could draw a perfect square on the ground using little more than a long, knotted rope. By creating a 3-4-5 triangle, they could guarantee a perfect 90-degree corner every single time. This was not advanced calculus, it was applied wisdom, turning abstract mathematical truths into the very bones of a building. This knowledge was so powerful it was often considered sacred, a way to mirror the perfect order of the cosmos here on Earth. With every block cut to a precise cubit and every corner set to a true right angle, the pyramid could rise with a confidence that echoed the stars. But these perfectly cut stones presented the next, and perhaps most visually staggering, problem of all. How do you move a block weighing as much as 2 elephants across miles of desert, and then lift it hundreds of feet into the air? That final ascent, dragging a block weighing as much as 2 elephants to the top of the growing pyramid, seems like an impossible task. The solution was not sheer muscle, but a profound understanding of physics. Builders mastered the inclined plane, a simple yet revolutionary technology. Picture a massive earthen ramp, its gentle slope winding its way up the side of the structure. By creating this long, gradual path, workers transformed an impossible vertical lift into a manageable, though still arduous, horizontal pull. They were trading distance for force. Instead of needing the colossal strength to lift a stone straight up, they could apply a smaller, sustained effort over a longer journey. This single principle made the construction of the highest levels achievable. Alongside the ramp, another simple machine was at work, the lever. With a long, sturdy wooden beam and a pivot point, a small team could perform feats that defied their individual strength. They could nudge a multi-ton block into its perfect, final position with the delicate precision of a craftsman setting a jewel. This was not about brutal force, it was about intelligent force. The widespread use of these machines points to a society that valued cleverness. It suggests a workforce of skilled laborers who understood the mechanics of their tools, not just a mass of laborers driven by punishment. They were solving problems with intellect, using the fundamental laws of the natural world to reshape their own. Once a stone was finally in place, the work of turning these individual blocks into a single, unshakable monument began. The stone itself had to be tamed. After solving the puzzles of movement and alignment, builders faced the raw material, a challenge of pure craftsmanship. Iconic walls, where massive stones fit together so perfectly that not even a razor blade can slip between them, were not born from luck. They were the result of deliberate, ingenious stone working techniques developed over generations. Without modern diamond-tipped saws, how did they achieve such impossible precision? They fought stone with stone. To shape a giant block of granite, workers used even harder rocks like dolerite. They would pound the surface repeatedly, a method called pecking, slowly and patiently fracturing the granite along its natural crystalline lines. It was a battle of persistence, slowly convincing the stone to take the desired shape. For a finer finish, they moved to grinding, using sand and water as a primitive abrasive to smooth the surfaces to an almost glass-like flatness. This was not just about creating a beautiful wall. This meticulous dressing of each stone's face was a matter of structural integrity. When two perfectly flat surfaces meet, the contact area between them is maximized. The weight of the entire structure above is then distributed evenly across this vast, intimate plane of contact. This interlocking puzzle of stone, often carved with subtle curves and protrusions that made the joints even stronger, created stability that rivaled modern concrete. The wall became a single, unified mass capable of bearing immense loads for millennia. Yet, even these masterfully fitted stones were sometimes given one final, unifying embrace. Yet, even the most perfectly carved stone is useless on unstable ground. The invisible foundation beneath a monument was its first and most important test. Before a single block was laid, builders had to confront the earth itself, ensuring it would not shift or settle under thousands of tons of weight. This was a battle against time and the elements, fought with simple yet brilliant techniques. In some places, they excavated down to the bedrock, creating a level platform that was part of the living planet. In softer soils, they might compact the earth with heavy stone rollers or even drive wooden piles deep into the ground to create a stable artificial base. The foundation trench for the Great Pyramid, for instance, was cut with such precision that its corners are nearly a perfect right angle, and its base is level to within 2 centimeters across its entire vast expanse. This obsessive attention to what would remain unseen reveals a profound understanding of structural forces. They knew that a towering building is a partnership between human ambition and the patience of the land. A structure is only as strong as the ground it stands on, a principle that remains true for every skyscraper built today. With a stable foundation and perfectly fitted stones, the structure could finally rise. But to protect their creation from the relentless forces of wind and rain, builders turned to chemistry, developing the silent partner of stone, the first strong mortars and binders. While some cultures perfected the art of dry stone construction, others pioneered the creation of adhesives that would hold their world together. The Romans are famed for their concrete, a material so durable it has survived millennia in seawater. But long before them, early civilizations were mastering the chemical transformation of common materials. In Mesopotamia, builders used bitumen, a natural tar that seeped from the ground, as a powerful waterproofing agent and adhesive. In Egypt, they developed gypsum and lime-based plasters. The process of making lime mortar was itself a small miracle of early technology. Workers would burn limestone in hot kilns, driving out carbon dioxide and leaving behind a powdery, reactive substance called quicklime. When mixed with water, this powder would undergo a violent, heat-producing reaction, slaking into a paste that could be combined with sand. As this mortar was used and exposed to the air, it would slowly reabsorb carbon dioxide, turning back over centuries into a solid, stone-like mass. This was a material that could set hard and endure for ages, allowing for greater flexibility in design and sealing structures against the weather. The creation of a durable adhesive was a quiet revolution, a vital partner to the stone itself. With solid materials and reliable binders now secured, the final challenge became one of pure logistics, the monumental effort of coordinating the entire operation from quarry to sky. A structure's true strength is forged in what remains unseen, buried deep beneath the sand. This was the sixth breakthrough, a mastery of foundation engineering that turned unstable earth into an unshakable partner for their ambition. Early builders understood that the ground itself had to be transformed. They would dig deep foundation trenches, then carefully fill them with alternating layers of compacted rubble, gravel, and sand. This ingenious method acted like a shock absorber, distributing the immense weight of the walls above and preventing uneven settling that could crack the entire monument. In regions with soft, wet ground, they drove long wooden pilings deep into the earth, creating a stable artificial raft that could support their colossal creations. But perhaps the most brilliant adaptations occurred where the earth itself was unstable. In earthquake-prone areas, builders designed foundations with a degree of planned flexibility. They used interlocking stone blocks that could shift and settle slightly during a tremor, absorbing the energy without causing a catastrophic collapse. This was not rigid resistance, but a clever, dynamic dance with the forces of nature. The foundation of the Great Pyramid stands as a timeless example of this obsessive precision. Its builders excavated down to the solid limestone bedrock, then leveled this vast platform to within 2 centimeters of perfect flatness across its entire 13-acre base. This invisible, painstaking work, hidden from all admiring eyes, was the non-negotiable first step. It was a declaration that this structure was not just built on the land, but was now a permanent part of it. With this profound stability secured from the ground up, architects could finally turn their minds to the ultimate challenge of elevation, designing a form that would defy gravity itself for thousands of years. The shape of a pyramid speaks a silent language of stability. Its wide base and narrowing peak are more than an iconic silhouette. They are a masterclass in applied physics, a lesson carved in stone for the ages. Early builders, through generations of observation and sometimes costly error, discovered a fundamental truth: to build high, you must first build wide. A broad base dramatically lowers the entire structure's center of gravity, anchoring it firmly to the earth. Think of a mountain, its immense weight rooted deep below the surface, unshakable by the fiercest winds. The pyramid mimics this natural form. Its inward sloping walls do more than define its shape. They act as a continuous funnel, guiding the colossal weight of every single stone downward, channeling those immense compressive forces in a straight, efficient path directly into the waiting foundation. This was an early, brilliant form of architectural calculus, an intuitive grasp of load distribution that meant the entire structure worked in harmony with gravity, not against it. The stability this form provided was not just for stillness, but for survival, making these towers of stone resilient against the relentless push of desert winds and the occasional shudder of the earth itself. Yet this powerful external form was only half of the story. To truly conquer height, builders had to look inward, designing a hidden skeleton that would lock the entire massive form together from the inside out. That powerful external form was nothing without a hidden skeleton. Inside the massive walls of the earliest elevated structures, builders engineered a secret support system using a technique called corbelling. Imagine a stack of books where you deliberately shift each new book a little bit inward over the one beneath it. That is the essence of corbelling. Builders would lay stones in horizontal courses, with each new layer projecting slightly beyond the one below, slowly and steadily narrowing the gap above. This gradual stepping inward allowed them to create doorways, roof spaces, and even entire chambers, all without needing a single arch. The weight from above was transferred down along these stepped layers, channeling the immense forces safely into the walls on either side. It was a way to cheat gravity, to create an empty space within a mountain of stone. But the walls themselves also needed internal reinforcement. Often, the outer faces of a massive wall were made of beautifully fitted, giant stones, while the core was filled with a carefully packed mix of rubble and mortar. This was not just filler. This internal mass acted as a continuous buttress, a hidden spine that distributed stress and prevented the outer walls from bulging outward under the colossal weight they supported. The legendary Cyclopean walls of Masonry are a perfect example. Their gigantic, irregular limestone blocks were fitted together with astonishing skill, but their true strength came from the packed rubble and earth within. This created a monolithic mass that moved and settled as one single, incredibly resilient unit. These hidden internal frameworks were the unseen marvels, the architectural sinew that gave these ancient giants the strength to stand for ages. Yet, while these methods could create towering walls and sturdy tombs, they presented a fundamental limitation for the spaces within. How could you create a wide, open room without the walls collapsing inward? The answer would eventually arrive in a shape that changed architecture forever. Conquering empty space was the final frontier for these early architects. They had mastered walls and foundations, but how do you put a roof over a vast chamber when wood is scarce and stone is your only tool? The answer was not a single invention, but a fascinating evolution of form. One of the earliest solutions was the corbelled arch, a technique of breathtaking patience and precision. Picture the magnificent treasury of Atreus, its great tomb not built with a true arch, but with concentric rings of stone, each circle carefully stacked and slightly offset inward from the one below. Layer by layer, these rings climbed upward, narrowing the space until the final, single capstone could seal the entire structure. The result was a soaring, beehive-shaped chamber, a space that felt both immense and intimately enclosed, all created without a single piece of timber. For smaller spans, builders turned to the brute strength of the lintel, a single, massive slab of rock laid across two upright supports. Think of the iconic trilithons at Stonehenge, where these colossal stone beams create doorways to the sky. Yet the lintel had a clear physical limit, the immense tensile strength of the stone itself, which restricted how wide an opening could be without the central span cracking under its own weight. The true revolution came with the development of the vault, an extended arch that could create covered corridors and long, narrow rooms. This was no longer just about covering a hole in the ceiling. It was about defining entire interior landscapes in stone. Each of these roofing methods, from the stepped corbel to the graceful vault, represents a different conversation with gravity. They reveal a society in continuous dialogue with the limits of its materials, constantly experimenting to create not just sturdy shelters, but awe-inspiring spaces for ceremony and power. This architectural ingenuity, however, would have been meaningless without a machine of a different kind operating on the ground. A masterpiece of organization that fed, housed, and directed the army of builders. The true scale of these monuments becomes clear when you realize the workforce itself was a marvel of engineering. This was not a story of endless toil by masses of slaves, but a triumph of social organization, a machine built of people. Tens of thousands of skilled laborers, from stonemasons to carpenters, worked in coordinated shifts. They were not driven by the lash, but by a system of state support that recognized their value. This army of builders was largely composed of farmers who worked on the monuments during the inundation season when the Nile's floodwaters covered their fields, turning a period of agricultural pause into one of national construction. This required a logistical miracle of its own. Detailed records from scribes preserved on fragments of papyrus and pottery show a breathtaking level of administration. They meticulously tracked everything from the daily bread and beer rations for a specific work gang to the delivery of precisely cut stones from quarries hundreds of miles away. Each worker had a role, each team a quota, and the entire operation ran on a river of information as vital as the Nile itself. This human machine was housed and cared for in sprawling barracks cities built near the construction sites. Archaeologists have uncovered evidence of bakeries capable of feeding thousands, infirmaries for treating injuries and illness, and even facilities for fish processing. Providing this level of care was not an act of charity, it was a strategic necessity. A healthy, well-fed worker was a productive worker, and a project spanning decades depended on a stable, returning workforce. This ability to manage such a vast human resource, to house, feed, and direct it with precision for generations, was a technological breakthrough as profound as the lever or the ramp. It was the invention of the project itself, a demonstration of early statecraft that could marshal the entire nation toward a single, skyward goal. But coordinating this human force was only half the battle, for it had to be perfectly synchronized with the steady arrival of materials from across the land. The journey of a single stone from a distant quarry to its final resting place high on the pyramid was a story in itself. Obtaining the perfect granite or limestone often meant traveling hundreds of miles. The Egyptians, for example, sourced their most prized granite from quarries near Aswan, an incredible distance from the building site at Giza. How did they move these multi-ton blocks across such a vast expanse? They turned the river into their highway. During the annual inundation of the Nile, when the floodwaters spread across the land, they would load the massive stones onto specially built, colossal barges. This was not a simple matter of floating a log downstream. It required a profound understanding of hydrology, knowing the river's currents and depths, and an advanced knowledge of boat building to create vessels strong enough to carry such an immense, concentrated weight without splintering apart. This was the first crucial link in a supply chain of breathtaking complexity. Once the stone reached its destination port, the challenge shifted to land. Without the wheel for heavy transport, workers used wooden sledges. They did not simply drag these sledges across the sand. Archaeologists and historians suggest they created prepared tracks, sometimes lubricating the path with water or a slurry of wet clay to dramatically reduce friction. A small team could then move a block that would otherwise have required hundreds. This entire operation, from the quarry foreman's first mark to the mason's final chisel stroke, was a monumental feat of coordination. It demanded forecasting needs years in advance, maintaining a vast inventory of tools and ropes, and orchestrating a continuous, rhythmic flow of materials to ensure the workforce was never idle. The silent, steady arrival of stone at the base of the pyramid was the heartbeat of the entire project, a rhythm maintained by countless unnamed planners and logisticians. This successful transport of materials set the stage for their final, precise placement, a delicate dance of positioning that required one last set of ingenious tools. The colossal ramps snaking up the sides of a pyramid were temporary mountains of human ingenuity. These vast, sloping roadways, constructed from mud brick, packed earth, and rubble, were the functional arteries that kept the entire project alive. They transformed an impossible vertical lift into a long, arduous, but manageable climb. The exact design of these ramps remains one of archaeology's great puzzles. Some researchers propose a single, straight ramp rising directly from the quarry, while others suggest a more complex zig-zag pattern that reduced the slope's steepness. Another compelling theory involves a ramp that spiraled around the pyramid's rising faces, a continuous corkscrew path to the sky. Each design presented its own challenges, balancing the need for a gentle slope against the staggering volume of material needed for the ramp itself. To make the climb possible, builders employed a simple yet brilliant tool beneath the sledges, wooden rollers made from felled tree trunks. These rollers acted like a continuous, moving pathway, drastically reducing the friction that would have otherwise made the task impossible. This entire system, from the ramp's gradual incline to the rolling logs, was a masterclass in mechanical advantage. It was the practical application of a fundamental truth, trading a long, gentle pull for a short, impossible heave. This principle allowed a team of workers to achieve what would have required the strength of hundreds, moving stones to dizzying heights one patient step at a time. Yet as the pyramid reached its final stages, the space at the top became desperately confined, and the ramps themselves began to block the very structure they were building. The final act of construction demanded a different kind of lift, a direct and precise hoisting of the last precious stones into place. The final ascent of a stone demanded more than just a ramp and a sledge. At the very top, where space was cramped and the margin for error was zero, a different kind of control was needed. The invention of strong, reliable rope was a quiet revolution in this high-stakes environment. Early civilizations mastered the art of turning plants into power, weaving papyrus, flax, or palm fibers into cords of immense strength. By simply looping these ropes over a sturdy wooden beam, workers unlocked a fundamental mechanical advantage. They could now pull downwards using their own body weight and the stronger muscles of their legs and backs, rather than trying to lift upwards in an awkward, unstable motion. This downward pull was not only more powerful, it was dramatically safer, giving a team the fine control needed to nudge a multi-ton block into its perfect, final position hundreds of feet in the air. The quest for stronger cordage was a continuous technological pursuit, a race to lift heavier loads higher and with greater confidence. Yet, this newfound lifting power presented its own delicate problem. Guiding a swinging, massive stone onto a precise target required one last, brilliant innovation. The final inches were the most critical. After a colossal journey, a stone block now rested near its intended home, but near was not enough. For the structure to achieve its legendary stability, the fit had to be perfect. This is where the brute force of ramps gave way to the delicate art of fine-tuning. Builders employed ingeniously simple wooden devices called cradles or rockers. They would carefully slide these curved wooden frames beneath the stone's edge. With a team applying coordinated pressure, they could then rock the entire multi-ton block back and forth, nudging it forward a tiny fraction of an inch with each gentle, controlled motion. It was a patient, rhythmic dance, a conversation between human intention and immense weight. For the very last adjustments, they turned to smaller levers made of sturdy wood or bronze. These were inserted into pre-cut gaps or against neighboring stones. A slight push on the long end of the lever would translate into a microscopic shift at the stone's face, a level of precision that seems impossible without modern machinery. This entire final stage was a testament to the builders' deep, intuitive understanding of their materials. They knew how much force a wooden lever could take before splintering, how to balance a stone on its rocker without it tipping, and exactly when to stop the moment of perfect contact. The proof of their success is etched in stone across the ancient world. Look at the inner chambers of the Great Pyramid, where granite blocks weighing dozens of tons are joined with seams almost invisible to the eye. Or consider the mighty walls of Sacsayhuaman in Peru, where gigantic, irregularly shaped stones fit together in a complex, interlocking puzzle, their surfaces so precisely matched that they have withstood centuries of earthquakes. This was not just construction, it was the final, masterful act of precision engineering, the quiet click of a lock that secured these monuments for eternity. That gleaming white skin of the pyramid was its final, perfect garment. While we picture the Great Pyramid as a stack of golden blocks, it originally looked utterly different, sheathed in over 5 million metric tons of brilliantly polished Chora limestone. This was not a mere decorative facade, it was the ultimate expression of the builder's precision. Each immense casing stone was cut with such phenomenal accuracy that the joints between them were often less than a millimeter wide, thinner than the edge of a coin. To achieve this on a structure of such immense scale was a technological triumph that pushed their established tools to the absolute limit. The process began deep in the quarries of Chora, where workers had to extract these enormous, flawless slabs without a single crack. Transporting these delicate, polished behemoths required even greater care than the core stones, a slow and deliberate journey to protect their pristine surfaces. Then came the true test, fitting each one to the growing pyramid. The standard plumb bob and level were used with an almost obsessive rigor, ensuring that as each new course of casing stones was added, the perfect, smooth plane of the pyramid's face was maintained. A single misaligned block would break the seamless flow from base to peak. This outer skin served a vital purpose beyond its dazzling beauty. It acted as a protective shield, a continuous, impermeable barrier that defended the softer inner core stones from wind, rain, and the relentless desert sun. The fact that most of these stones were eventually removed for other buildings over the centuries only deepens the mystery. It reveals the breathtaking gap between the weathered monument we see today and the shimmering, almost otherworldly vision it once was, a man-made mountain of light. This pursuit of a perfect external form was not unique to Egypt, as a journey to the Americas reveals a completely different philosophy for achieving the very same goal. In the high Andes, the ground itself is rarely still. The Inca built their empire in a landscape constantly reshaped by tremors, a relentless challenge that demanded a completely different architectural philosophy. Where others sought rigid, unyielding permanence, the Inca embraced intelligent flexibility. Their breakthrough was not in a single tool or material, but in the very shape and relationship of each stone. They selected massive, irregular blocks of granite and andesite, then worked them with stone hammers and abrasive sand until every edge, every curve, was a unique masterwork of geometry. These stones were not simply stacked, they were keyed together in a colossal three-dimensional puzzle, with interlocking protrusions and recesses that defied visual inspection. The walls they formed leaned subtly inward, a quiet nod to the pyramid's principle of a low center of gravity, yet they used no mortar whatsoever. This was the secret. When an earthquake strikes, a rigid mortar-bound wall will crack and crumble as it fights the motion. But an Inca wall is designed to move. The stones in their dry stone construction are free to shift and shudder, to dance with the Earth's energy for a few critical seconds. Then, as the tremor subsides, gravity and those perfectly carved interfaces guide each block precisely back into its original position. This dynamic stability is a breathtaking example of building in harmony with nature's chaos. The Inca solution proves that the pinnacle of engineering can be found in form and fit, a resilient partnership between stone and earth that has withstood centuries of tectonic conversation. This principle of adapting to the environment resonates far beyond the mountains, appearing in the very cradle of civilization where another culture confronted a different, yet equally demanding landscape. The land between the rivers offered no quarries of stone, only endless plains of mud. Yet from this humble material, the Mesopotamians engineered their own path to the heavens, the ziggurat. Their breakthrough was not in moving mountains, but in reinventing the very brick they walked upon. They learned that by mixing river clay with chopped straw, they could transform a fragile mud block into something far more resilient. The straw acted as a microscopic reinforcement, a web of fibers that distributed stress and prevented the bricks from cracking as they dried and shrank. This was an early form of composite material, a clever solution born from necessity. For the outer skins of their most important structures, they took this process a step further, firing the bricks in kilns. The intense heat permanently altered the clay's chemistry, turning it into a durable, weather-resistant ceramic. Building a monumental structure from millions of these hand-sized units required a different kind of vision. The ziggurat was a masterpiece of layered design, a massive stepped pyramid where each level was a smaller platform resting on the one below. This created the essential broad base, anchoring the entire temple to the earth. But even these fired bricks needed protection from the rare but torrential rains. The final shield was often a layer of bitumen, a natural tar that was heated and applied as a waterproof sealant, effectively creating a massive, primitive damp-proof course. This entire process, from strengthening the brick with straw to sealing the facade with tar, represents a profound understanding of material science. It proves that the drive to build high was not dependent on a single resource like stone, but on human ingenuity. The ziggurat stands as a testament to building with what you have and perfecting it through intelligence and patience. In the absence of granite, they mastered mud, and in doing so, they reached for the gods just the same. The stars themselves became a master blueprint for the builders. While earthly tools defined the plumb line and the level, the cosmos provided the ultimate fixed reference, a celestial grid against which they could map their ambitions onto the earth. The legendary alignment of the Great Pyramid's base with the cardinal directions is a feat that still inspires awe. Its sides run almost perfectly north-south and east-west, with an error of less than 1/15th of a single degree. This was not an accidental achievement or an act of faith alone. It was the result of meticulous, long-term astronomical observation. One compelling theory suggests that ancient surveyors used a simple, yet profoundly effective, method involving a circular wall and a central gnomon, a vertical rod. By tracking the shadow of this rod over the course of a year, they could mark the points of the shortest and longest shadows, which correspond to the solstices. By bisecting the angle between these 2 points, they could find a precise true north-south line. This single, perfectly oriented baseline was the foundational stroke from which the entire geometric perfection of the pyramid grew. Every right angle, every square corner, all depended on this initial celestial truth. This practice wove the fabric of the universe directly into the stone. The structure was not merely built on the land, it was anchored to the cosmos, a terrestrial mirror of a celestial order. This deep connection reveals a world where technology and philosophy were one, where the highest purpose of engineering was to harmonize human creation with the eternal rhythms of the heavens. And just as they looked to the stars for perfect alignment, they also learned to listen to the subtle whispers of the earth beneath their feet. A pyramid was not just a structure of stone, but a structure of thirst. The sheer scale of labor required a constant, reliable supply of water, a logistical challenge that rivaled the movement of the stones themselves. For the thousands of workers concentrated at a single site, water was not a luxury, it was the fuel of the entire operation. It was needed for drinking, for cooking, for the basic needs of a small city living in the desert, but its role extended far beyond sustenance. Water was an essential tool. It was mixed with gypsum and sand to create the plasters and mortars that sealed structures. It was used to cool the bronze drills and saws that grew hot from friction as they cut stone. Without a sophisticated system to manage this vital resource, the grandest architectural plans would have quickly turned to dust. This led to one of the most practical yet brilliant breakthroughs, the development of on-site hydraulic engineering. Teams dug deep wells to tap into groundwater, constructed canals to divert water from the nearest river, and built vast plaster-lined cisterns to store it for the dry seasons. At the Minoan Palace of Knossos, for instance, advanced stone-lined conduits and terracotta pipes provided running water and managed waste with a sophistication that would not be seen again in Europe for over 1,000 years. This mastery of hydraulics was the silent, invisible system that kept the heart of the construction site beating. One of its most clever applications was in the very first stage of building. How could you ensure a foundation trench several acres in size was perfectly level? The answer was to use water's own unwavering nature. Workers would dig a network of interconnected trenches across the bedrock base and then carefully flood them with water. By marking a consistent water level on the trench walls, they could establish a universal horizontal plane across the entire, vast site, a simple yet infallible method for achieving a perfectly level foundation. Every tool that touched stone, from the mason's chisel to the massive saws, relied on this managed water supply to function effectively. The rhythmic striking of stone on stone created intense heat, and without a constant stream of water for cooling, metal tools would soften and lose their edge, while stone dust would choke the air and the workers. Water was the great enabler, the fluid partner to solid rock, making the entire monumental effort not just possible, but sustainable for the decades it took to complete. A single stone from quarry to sky passed through dozens of expert hands. This was not a task for general laborers, but for a symphony of specialized masters. Monumental construction created a new class of professional, the lifelong artisan whose entire world was dedicated to perfecting one crucial skill. The master stonecutters did not simply break rock, they read it. They understood the hidden grain and fracture lines within a block of granite, knowing exactly where to strike to cleave it with controlled precision. The carpenters were not just woodworkers, they were structural engineers in timber, designing the massive ramps, the intricate lever systems, and the formwork for plaster and concrete that would shape the final monument. The toolsmiths forged and sharpened the bronze chisels and saws, understanding the metallurgy needed to keep an edge against unyielding stone. Rope makers transformed plant fibers into lifelines of immense strength, their intricate weaving techniques a matter of life and death for teams working at great heights. Each of these roles represented a deep, accumulated knowledge that could not be learned quickly. This wisdom was a treasure, most often passed from parent to child within family lineages or protected guilds. A father would teach his son not just how to hold a chisel, but how to listen to the sound it made against the stone, a subtle pitch that indicated a clean cut versus a dangerous crack. This generational transfer created a living library of technique, where each generation could refine and improve upon the methods of the last. Why was this division of labor so transformative? It allowed for a staggering leap in efficiency and quality. A worker who spent his entire life making rope became an undisputed expert in tensile strength and durability. A surveyor who dedicated his career to aligning walls with the stars could achieve an accuracy that seemed supernatural. This specialization meant that every component of the project, from the strongest cord to the most perfectly angled block, was produced by someone who had devoted their life to that single, perfect outcome. The existence of these specialized, non-farming professions signals a society of remarkable complexity and economic strength. It meant the community produced enough surplus food to support an entire class of people who did not work the land, but instead worked to turn collective ambition into reality. This human capital, this investment in lifelong skill, was the invisible engine behind every physical tool. The true monument was not just the pyramid that rose from the desert, but the enduring legacy of craftsmanship that built it. The grand vision began not with a mountain of stone, but with a small, handheld model. Before a workforce could be assembled or a quarry opened, the entire project had to exist in the mind of the architect, and they needed a way to share that vision. We find evidence of this crucial first step in surviving artifacts, intricate scale models carved from wood or molded from clay. These were not mere toys, they were functional prototypes, three-dimensional blueprints that allowed a master builder to test proportions, visualize the interplay of masses, and identify potential structural weaknesses long before they became catastrophic flaws on the building site. This act of miniaturization was a profound cognitive leap. It required the architect to hold two realities in their mind at once: the small, tactile object in their hands and the colossal, future reality it represented. They could point to a tiny clay wall and say, "This must be 10 cubits thick," or trace the path of a model corridor and foresee a logistical bottleneck. This pre-visualization was a form of risk management, saving immense amounts of time, resources, and effort by solving problems in the safe, quiet space of the planning room. While few full architectural plans on papyrus have survived the millennia, tomb paintings show us the tools of this translation process. We see the architect, a coiled measuring cord in his hand, the very same cord used to create perfect right angles on the ground, now being used to take dimensions from a model or to mark them out on a fresh sheet. Beside him, a scribe diligently records every number, every ratio, transforming spatial ideas into lists of instructions. This was the birth of the specification document, a set of commands that would allow teams working miles apart to create components that would fit together perfectly upon arrival. This seamless flow from a miniature idea to a world-altering structure is a testament to a new kind of thinking. It is the same fundamental process used by every modern architect and engineer today, a direct lineage of planning that connects a clay model in ancient Egypt to the digital renderings of a contemporary skyscraper. With a design finalized and committed to plan, the focus could shift from the abstract to the physical, confronting the fundamental laws that would determine whether their vision would stand or fall. That silent library of knowledge was not written in books, but etched into the very stone they chose. Early builders engaged in a continuous, hands-on dialogue with their materials, learning their unique languages through trial, observation, and the hard lessons of structural failure. They may not have known the physics equations for compressive strength, but they knew instinctively that a dense granite could bear a far greater load than a soft sandstone. This was a deeply empirical science, a database of practical knowledge built over generations. They learned which stones resisted weathering, which types of wood were flexible yet strong for levers, and precisely how to mix a mortar that would set hard in a dry climate versus one that needed to remain slightly flexible in an earthquake zone. This understanding directly shaped their designs. You can see this wisdom in the Great Pyramid itself, where the massive, weight-bearing inner chambers are constructed from immense blocks of granite, a stone of incredible compressive strength hauled from quarries hundreds of miles away. Yet the vast core of the pyramid is filled with local limestone, a softer, more readily available material perfect for the infill that did not bear the same direct, concentrated load. This was not a random choice, it was a strategic application of material science. They placed the strongest resources where the stress was greatest, a principle that remains at the heart of all modern engineering. This practical knowledge constantly intersected with the abstract beauty of mathematics. A builder knew that a stone of a certain size and density had a predictable limit, and this physical reality informed the geometric ratios they used. The strength of the material gave them the confidence to design the form, and the elegance of the form ensured the material would not be pushed beyond its breaking point. This interplay between the tangible and the theoretical was their true blueprint, a partnership of hand and mind that turned local rock into eternal monuments. The silent strength of a triangle found its voice in the forests, in lands rich with timber, from the longhouses of northern Europe to the great halls of ancient China. Builders engineered a different kind of ascent. Their breakthrough was not in piling stone upon stone, but in weaving wood into a resilient, weight-bearing skeleton known as the truss. This rigid framework of beams, arranged in powerful geometric patterns, was a quiet revolution in understanding forces. A shaped truss, for instance, masterfully channels a roof's downward weight. The horizontal beam at its base resists the outward push, enduring tension, while the angled beams above handle the crushing force of compression. This clever distribution of stress meant that a structure could achieve wide, open interiors without the need for forests of internal support columns. It was a way to create vast, unobstructed spaces for gathering, for ceremony, for community, all sheltered under a roof that seemed to float on a lattice of wood. This knowledge of how to make a flexible material like wood behave with the rigid strength of stone was a parallel technological track, every bit as sophisticated as stone corbelling. The principles of triangulation and bracing learned in the carpenter's yard would eventually travel, informing the design of stone bridges and the flying buttresses of Gothic cathedrals centuries later. It proved that the ambition for grand, elevated space was universal, whether the primary tool was an adze or a chisel. Yet these physical innovations in wood and in stone were fragile. They lived in the hands and minds of the artisans. A single generation gap, a war, a famine, and this hard-won knowledge could vanish as completely as a city in the sand. The ultimate challenge, then, was not just to invent these techniques, but to make them immortal. The final and most vital tool was not made of wood or bronze, but of human connection. The master builder's most profound skill was not in his own hands, but in his ability to teach. In an age without formal engineering manuals, the entire library of architectural genius, every technique for dressing stone, aligning walls, and tying a knot that could hold the sky, existed only in the memories and muscles of living artisans. This knowledge was transmitted through a sacred chain of apprenticeship, a slow and intimate passing of the torch from one generation to the next. A young student would spend years at his master's side, not just being told how to do things, but absorbing the subtle, unwritten lore of the craft. He learned the exact sound a chisel should make when it strikes granite correctly, a sharp, clean ring versus a dull, worrying thud. He developed a feel for the slight drag of a level that indicated an invisible slope. These were intuitions that could never be captured in a written instruction. This system created a living, breathing repository of technique, a resilience that protected these hard-won secrets from being lost to time. A single master might hold the key to a unique quarrying method or a revolutionary lever design, and his legacy was the handful of students he trained to the same exacting standard. This made technological progress beautifully cumulative, with each generation building upon the refined wisdom of the last, yet it was also dangerously fragile. A war, a famine, or a single broken lineage could erase centuries of innovation in a single season, leaving later civilizations to stare at the mute stones and wonder how such wonders were ever possible. This human network was the invisible glue that bound all the other breakthroughs together, the ultimate safeguard for a society's most precious resource, its knowledge. The legacy of these ancient builders, then, is far more than the monuments they left behind. It is a powerful reminder that our greatest structures are always, in the end, built upon a foundation of shared wisdom and trust. The spirit of the ancient builder lives on in the shadow of every modern skyscraper. The tools may have changed, but the fundamental principles they first discovered are now the bedrock of our entire built world. Pick up a modern spirit level, and you are holding the direct descendant of the water level and Plumb, a tool that still uses the unwavering force of gravity to define what is true. The design of every massive dam and towering high-rise consciously applies the ancient lesson of the pyramid, that a wide, stable base is non-negotiable for reaching great heights. This is not a coincidence, it is a direct lineage of knowledge. Our own sophisticated concrete, the material that shapes our cities, builds upon millennia of experimentation, from the gypsum plasters of Egypt to the legendary Roman concrete that endures in maritime piers. The legacy is not just in what we still use, but in what we are still learning. Modern seismic engineers study the interlocking stonework of the Inca with profound respect, seeing in their flexible, dry stone walls a masterclass in designing structures that can dance with an earthquake rather than resist it to the point of collapse. These are not forgotten secrets but a living foundation. They teach us a powerful truth about human progress, that our greatest leaps forward are often built upon the patient, accumulated wisdom of the past, refined across generations. This enduring connection between ancient intuition and modern science invites a final, forward-looking question. If these builders could achieve so much with so little, what does our own future of construction hold? And what new principles will we discover to build even higher and even smarter for the world to come? Even the most brilliant achievements of the past hold onto their final secrets. For all we have uncovered about the Great Pyramids, the precise configuration of the construction ramps remains one of history's most tantalizing puzzles. Was it a single, monumental straight ramp, a more efficient zigzag path, or a spiraling roadway corkscrewing up the rising faces? Each theory presents its own logistical challenges, and the absence of definitive archaeological evidence keeps this debate alive and vibrant among researchers. This is not just an academic exercise. The choice of ramp design speaks volumes about the ancient project manager's mind, revealing their intricate balancing act between slope, volume, and the sheer human effort required to reach the sky. This same shroud of mystery envelops the massive stone heads of Easter Island. How were these colossal moai, some weighing over 80 tons, transported miles across the island's rugged terrain and then erected on their stone platforms? Oral traditions and modern experiments suggest various methods, from a rocking motion that walked the statues forward to the use of wooden sledges on prepared tracks, yet a conclusive answer still eludes us. These are not isolated riddles. They are reminders that our current understanding is a snapshot, constantly being refined by the light of new tools. Today, technologies like LiDAR scanning are peeling back the forest canopy to reveal entire lost cities hidden for centuries, while muon radiography acts like a cosmic X-ray, allowing scientists to peer deep inside solid stone pyramids to detect hidden chambers and voids without ever touching a chisel. Each of these non-invasive techniques promises a fresh revelation, a new piece of the puzzle that could fundamentally rewrite our chapter on ancient ingenuity. The story of early elevated structures is far from a closed book. It is an active, ongoing investigation, a dialogue between the past and the future. The enduring allure of these questions, the simple fact that we are still searching for answers, is what keeps the field of historical mysteries so profoundly exciting, ensuring that the next great discovery is always just beneath the surface. From the simple plumb bob to the complex organization of thousands of workers, the technological breakthroughs of early civilizations were a symphony of ingenuity, perseverance, and a deep understanding of the natural world. They transformed ambition into stone and skyward aspiration into enduring reality. These structures stand not as relics of a primitive past, but as monuments to a sophisticated and creative human spirit. The lessons learned from their construction, from the physics of the inclined plane to the strength of shared purpose, continue to resonate in our own architectural endeavors. Every modern crane lifting a steel beam owes a debt to the first lever that nudged a block into place. Every project manager coordinating a team echoes the ancient scribe tracking deliveries of stone and bread. As we look up at their achievements, we are reminded of the incredible potential of human innovation when driven by a collective vision. We would love to hear which of these ancient breakthroughs you find most astonishing. Was it the celestial alignment of the pyramids, the earthquake-resistant walls of the Inca, or the social machine that fed and housed an army of builders? Share your thoughts in the comments below and subscribe for more journeys into the enduring mysteries of our